Let us begin our next section on relative motion with a scenario. Suppose that we have two people riding in a car and they drive by a third person who is on the street. How can we describe each of these separate velocities? That's what we're looking at when we're describing relative motion. The two people in the car have the same velocity of 0 meters per second. If we're talking about the velocity relative to each other. So say you're out riding in a vehicle with a friend. You both, relative to each other, have the same velocity, 0 meters per second. Relative if we're going to describe the velocity relative to the person on the street, we can say that the people in the car have a velocity of 10 meters per second. And why can we describe it like this? We can describe it like this because we're looking at different frames of reference. And depending on our frame of reference, motion may be described differently depending on the frame of reference. So it depends on if we're describing the motion inside the car where the two friends are, or if we're describing our motion outside the car where the person is watching the car pass them. And that all leads us right into relative velocity. When we want to express a velocity, we must express in relation to a frame of reference. In other words, what we're going to see typically is we might have like VOG, and this is the velocity of our object that's being analyzed, and that will be relative to the ground. We will have velocity of the medium, the substance is passing through, relative to the ground. And we'll have our velocity of our object relative to the ground. And if we're looking to actually calculate the velocities, we would get the following equation that relates these velocities. Our velocity of the object in relation to the ground is equal to the velocity of our object relative to the medium plus the velocity of the medium relative to the ground. And if you're ever having trouble connecting those together, you will notice that the second letter in our first velocity is same as the first letter in our second velocity, which essentially cancels each other out, and that's the worst way I can say it, but essentially that's what's occurring. And then we have together to calculate the velocity of our ground, of our object relative to the ground. So let us see this in one actual example coming up here. A swimmer is trying to get from one end of the river by moving 8.23 meters per second east. And the river has a current of 3.6 meters per second north, and it's approximately 3,600 meters wide. And our question is asking us to find the velocity of the swimmer relative to the shore, determine how long it takes to cross, and where our actual landing position is. So as always, beginning a question like this is easy. We're just going to state that north and east is positive just in case. Let's roughly draw a diagram of what this would actually look like. We have a river that is approximately 3,600 meters wide. We have the swimmer that's swimming to the east. Let me just continue here. To the east at 8.23 meters per second. And then the current connecting tip to tail of our vectors, the current of the water is 3.6 meters per second north. And we need to figure out the velocity of the swimmer relative to the ground. So we shall make some variable declarations first. Let S represent the swimmer. Let G represent the ground or the shore. And let's let W represent the water. So, find the velocity of the swimmer relative to the shore. We know that the velocity of the swimmer relative to the water is 8.23 meters per second. And the velocity of the water relative to the ground in this case is 3.6 meters per second, and we see that right in the diagram. We must calculate the velocity of the swimmer relative to the ground. And let us look at our equation. This is what we're looking to solve for. This is what we don't know. So velocity of the swimmer relative to the ground. So we must start with the swimmer relative to the water. I forgot to mention 90-degree angle, so we know that we'll use Pythagorean theorem. Plus the velocity of the water relative to the ground, and you'll see that our W's essentially cancel out, so we are in fact calculating the velocity of the swimmer relative to the ground in this statement. So, therefore, this is going to be equal to the square root of 8.23 squared plus 3.6 squared, and we get an answer in this case of 9.0 meters per second. And because we have the 90-degree angle And because velocity is a vector component, we need to calculate theta. And just a quick reminder from trig, opposite and adjacent tells us we are going to use tan to calculate that angle. So that will be 3.6 over 8.23. So we'll take the inverse tan of that division. Which ends up being 24 degrees. So therefore, the velocity of the swimmer relative to the ground is 9.0 meters per second. Our first direction is east, 24 degrees north. Part B asks us, how long does this crossing take? How long does the crossing take? So we know from before in this question, for part B, that the displacement is in fact 3,600 meters, and the velocity of the swimmer in the water is 8.23 meters per second. How long does this take? So our time will be calculated by taking the displacement over the velocity of our swimmer, or 3,600 meters over 8.23 meters per second. 437 seconds is how long it takes. And we pay attention again to significant digits. Therefore, it takes 440 seconds. In this question, this number here is technically two significant digits. The trailing zero that's after our non-zero digits does not count as a significant digit in this case. In part C, we're looking for the landing position of the swimmer. We will remember that the swimmer crossed a river going in the east direction first that was 3,600 meters. And because of the river's current, it pushes our swimmer a bit to the north, some displacement north. Our displacement north can be calculated by the fact that we're taking the velocity of the water relative to the ground multiplied by how long the trip takes. And that will be 3.6 by 437 seconds. So displacement north is actually 1,575 meters in the north direction. So we can calculate what the actual displacement of the swimmer was. And again, we assume because north and east are perpendicular, 90 degrees. Therefore, by Pythagorean theorem, we can take our displacement, take the square of our displacement east and the square of our displacement north, and calculate where the landing position was. By taking the square root of both those added together, we get that the displacement was 3,929 meters relative to the starting position. Our theta in this case is still exactly the same as part A. So therefore, The landing position relative to the start was 3.9 times 10 to the 3 meters east, 24 degrees north. As always, if you had any questions about your homework, don't hesitate to email me, to ask on the discussion board, etc.